So to make a simple low-pass RC filter, you just put a resistor and a capacitor in series and take the output across the capacitor. So in this case, I have a sinusoidal voltage source, 3 volts peak to peak, and 6.8 kilo ohm resistor, and a 0.01 microfarad capacitor, which is the same as 0.01 times 10 to the minus 6 farads. So let's do some calculations to understand what's going on. The reactance for the capacitor we know is 1 over 2 pi Fc, where F is the frequency and C is the capacitor. So let's take an instance at 500 Hertz. If we plug into this equation and make the calculations, we get 31831 ohms, 31,831 ohms. Then we need to calculate the impedance of the whole circuit, so now we take into account the resistor and the capacitor, and that's given by Pythagorean theorem, so Z equals square root of R squared plus X sub C squared. So we make the substitutions and we get a result of 32,549 ohms. Now that we have the impedance, we can use that to calculate the current in the circuit. And in our case, we're using peak-to-peak values, so we have 3 volts as our voltage source divided by the impedance we just calculated, which is 32,549 ohms, and we get a current of 0.092 milliamps. Since that current is the same for all components in a series circuit, we can now calculate VC, the voltage across the capacitor, as the current times the reactance. So that's 0.092 milliamps times the 31,831 ohms that we had calculated before, and we get a result of 2.93 volts. While we're here, we might as well calculate the voltage across the resistor. So that's the current times the value of the resistor, you see there, and we get a result of 0.63 volts. So if I were to recalculate this at much higher frequencies, you can see that based on the X sub C equation, since it's inversely proportional to the frequency, X sub C would become smaller at higher frequencies. So likewise, V sub C would also be smaller at higher frequencies. So let's take a look at the physical circuit. So here we have the resistor and the capacitor in series connected to the oscilloscope. We can see here that our voltage source is the yellow curve, which shows 3 volts peak to peak, and the green is the output across the capacitor. You can see the green is slightly less than the voltage source, so we can say that's roughly 2.93, which is what we calculated. Now I have integrated into my oscilloscope the actual function generator, so I'm going to go in here into the frequency and vary it. So as I increase the frequency, you can see that the green curve, which represents the output of the capacitor, gets smaller. The higher I make the frequency, the smaller it gets. So what you would want to do is plot some points at different frequencies to see what the curve of the voltage across the capacitor looks like. It would be rather tedious to make a bunch of hand calculations, so what I've done is plugged this into an Excel spreadsheet and taken points at 500 Hertz, 1000, 1500, 2000, 4000, and 8000 Hertz, and done the calculations for VC and VR. So you can see on the chart there that the red line represents the voltage across the capacitor and the blue line represents the voltage across the resistor. So for low frequencies, if you look at the red around 500 Hertz and 1000 Hertz, you can see that the voltage is fairly high. And as you get past 3000, the voltage across the capacitor diminishes significantly. Conversely, the voltage across the resistor at low frequencies is low, and as the frequency increases, the voltage across the resistor also increases. So this is why the voltage across the capacitor would be considered a low-pass filter. At the low end of the frequencies, the voltage across the capacitor is high, and at the higher end of the frequencies, the voltage of the capacitor gets attenuated or diminished, therefore making it a low-pass filter. If you want to make a high-pass filter, all you have to do is switch the components and just take the voltage across the resistor. You still have a series circuit, and it's pretty much all the same equations. So if you look at the plot, now the voltage across the resistor at low frequencies gets attenuated, but at high frequencies the voltage across the resistor passes, therefore making it a high pass filter when you take the voltage output across the resistor. So let's take a look at the high pass filter on the oscilloscope. Once again, we have the signal source represented by the yellow curve, and the voltage across the resistor now is the green curve. So at low frequencies you can see that VR is rather small. If I go in here and increase the frequency, as frequency goes up, the amplitude of the voltage across the resistor also gets increased. Therefore, at higher frequencies, a higher amplitude is passed across the resistor, therefore making it a high-pass filter. And to summarize, you can make a low-pass filter by taking the voltage across the capacitor of an RC circuit, or you can make a high-pass filter by taking the voltage across the resistor in a series RC circuit.